at that point, and this is super nerdy stuff here, but we'll get into it. If you get into the front end noise of what limits the noise floor, right? What 47 dB is the front end devices of the 5510 will limit the noise floor.
Hey everybody, Dave Limerick in Hong Kong with another episode of THD Podcast. Thanks for tuning in. Please like, subscribe, all that good stuff. Today we've got Triad Semiconductor. They're out of West Coast US, and they've got a analog front-end component that seems to be able to handle any inputs. So we're going to find out all about that, and let's follow up on that. But without delay, the Alti Association, please encourage everybody to go check out their pavilion at the high-end show in Munich in June. So please go say hi to Barry and all his participants in that event. And also Audio Express, I know they've done some coverage on Triad, so please, if you like what you're finding out today, please follow up with Audio Express to find out more details about what we've been talking about. But without delay, let's say hello. We've got Simon Weston in Japan. Good morning, Simon.
Morning.
And we got Philip and Tony from Triad joining us. Good afternoon, guys.
Hey,
Good evening.
All right. So, yeah, you guys got a component that looks like it's pretty good for pro audio, but we'd like to find out some more. Let's talk about it.
Sure. So Triad as a company, we're not actually at the West Coast. I'm based on the West Coast, but the company's based out of North Carolina. So
all right. You guys have a medical background?
Phil, do you want to talk about that?
I started doing ASIC specs, started in 2002, actually. So our customer base from an ASIC perspective ranged from industrial to medical, military, automotive, consumer, kind of a full range. And this area is, however, is the first area that we're kind of investing in as standard products. And so we're excited about it. We have 25 years worth of really good analog differentiated building blocks as an ASIC company. We've trained our company to kind of listen to the market very carefully, listen to our customers. In an ASIC world, you don't make money unless you deliver a lot of value for that one customer. And you have to listen well, and you have to design well and execute. So that's what we have as a history. And Tony came on a few years ago with his expertise in audio to really help us kind of create some innovative products in this market. So it's exciting.
Okay.
So yeah, we have a few slides to share here. This is a little bit of company background. Phil talked to this already. We have a kind of a fairly mixed background in doing ASICs and mixed signal ASICs for people. Based out of Winston-Salem, North Carolina. So the preamp you mentioned. So this is our first real ASSP product in the market. It's called the TS5510. It was sprung out of some problems and some experience in designing for both for myself for pro audio and consumer audio, but especially in pro audio, you have this issue that many things get kind of plugged into XLR sockets on a pro audio device on a console. Some of them are very tiny signals, mic amps, some mics, that kind of thing. Some are very large, very high-level signals, analog synths, using an external mic preamp that you want to bring into the console, that kind of thing. Some things are balanced, some things are single-ended. When you plug in, you want them to be treated kind of the same or well. And long lines in like live venues and stuff, you have a lot of common mode interference. So there's that as well. So these are not new problems, but what we're kind of bringing to the table here is a new solution to some of the older problems. One of the things that's changed over the years is, I mean, back in the day when we were designing analog consoles, you took a signal in, you wanted the signal to be as big as humanly possible, get it to the EQ, get it to the rest of the circuitry in the console. These days, it's a little bit different in that you're bringing signals in. That's not changed. A lot of those sources are the same sources they ever were. What's changed is there's an ADC, and that ADC typically has a 2-volt RMS maximum input or a 3-volt RMS maximum input. It's not, plus or minus 15 volts that you're trying to get. You have to scale everything into that 2-volt RMS, 3-volt RMS kind of input range for the ADC to digitize. So you have a high gain requirement still, but a lot of the time now you have an attenuation requirement, right? You've got big signals coming in, you have to scale them down to get into the ADC and still retain signal to noise for that. The other thing as well that's changed is a lot of the, back in the day there was big studio furniture, right? Consoles were big. But nowadays, a lot of the applications and install applications as well as pro audio. The form factor is a big consideration, right? You got to fit this stuff in a very small space on the PCB. So.
Right.
So a lot of and getting into the kind of the guts of the preamp, right? So getting into what we're doing here. A lot of what's gone before in terms of mic preamps boils down to kind of one configuration, which is the instrumentation amp or INA topology. So you've got ICs out there that use this. You've got discrete implementations that use bipolars, that use low noise op amps. But really, they use the same configuration all the time. So that's fine. It's had its run, but there are some kind of limitations with that configuration. So what it looks like is when you break it down to a topological level, there's a really simplified kind of block diagram for this, is that you've got two amplifiers at the front, and they kind of amplify differentially, and then the A3 is the kind of second stage, which takes that kind of first differential stage, and sometimes it can, shown here to be single-ended. Sometimes, or typically for an ADC, you treat it differentially, and so you'd have a differential output on the second stage. So this is a little bit simplified just to explain things.
Hey, Tony, what this instrument amplifier? Why wouldn't you just put your differential signal straight onto A3, plus and minus?
Good question. So you may want to control the input impedance coming in. So you can switch that typically sometimes between high impedance and low impedance. If you just kind of get rid of the first stage, you're stuck with a medium level input impedance on that side. So, and typically for a mic amp, if you're plugging a mic in, that's not a real, just having that kind of second stage around A3, that's not a real good way to deal with the noise requirements of a mic amp. Typically you'd want to make RA, you imagine A1 and A2 weren't there, you'd have to make RA and just RA very low, which lowers your input impedance. So it's not typically done. You can do it, but it's not typically done. Yep. Which is why the first stage is there to give you that kind of high gain sort of, by making RG very tiny, you're not loading the mic amp at all. That whatever input impedance you've got is kind of is divorced from the Gesher gain setting through RG. Right. So that's typically why that's there.
Thanks.
Good question. And then, so differential signals go through. Common mode signals, however, they also go through the first stage. So if you imagine you've got a common mode signal that you want to reject, the only rejection by having this kind of A1, A2 configuration, great for mic amps, but anything that's common mode goes straight through, is amplified by A1, A2. You're relying on later stages in the design to kind of get rid of any common mode. So in this case, the matching of RA and RB on both sides gives you your common mode rejection before it hits the ADC. Some of the commercially available mic amps that you can buy now, they actually don't include that second stage, so they're reliant on the ADC own common mode rejection to kind of to do the work for you. So that can be a bit alarming. So what's wrong with this configuration, right? So it's it's been around for a while. If you start thinking about the attenuation problem, if you want to attenuate a signal down to a 2 volt RMS or 3 volt RMS to feed into an ADC, having that A1 and A2 kind of front end really isn't any help, because it can't attenuate things. It can only gain things up, or if you take RG out of circuit, like on the slide there, it's a unity gain thing. So you're relying then on the second stage, RA and RB, to reduce that or attenuate signals coming in. But that's not great either, because now you have to put all your gain variation on those that resistor chain that side. And typically what's done to accommodate this is to have a pad, or a resistive pad or a resistive divider on the front end before this. So none of the signals, none of the amplifiers on the latter chain see large signals. So you're kind of reliant on this being a unity gain or greater kind of block, and then having an attenuator on the front end, which works. But then you have to switch the attenuator in and out. So you have relays or FETs or more circuitry to do that. And also you have this discontinuity in gain selection, right? You can't have this continuous gain of this continuous variation from gain to high gain to high attenuation. So the second issue is really that thing I mentioned earlier. This is trying to show you that if you have a combination, because in real life you have a combination of signals you want, audio signals, and signals you don't want, which is the common mode. So, as I said earlier, the A1, A2 stuff is great for isolating the input, but it does mean that you have both common mode and differential signals flying around on those middle nodes. And so, if you're gaining up the front end, then you can run into because the common mode adds in, it actually can saturate internally in the system itself. So you get these A1 and A2 outputs can clip due to the fact they're carrying common mode. You don't see that common mode at the output, but what you see is the distortion from the common mode kind of adding in. So that's the kind of great topology used everywhere. They're the kind of shortcomings for it. So what did we do? So we rethought this a little bit, and so we looked at some old papers from 1968 from Cedra and Smith, who wrote a few papers around this. They used they were looking at different ways to use bipolars at the time and design things. So they came up with this Current-Conveyor technology. So briefly, what the Current-Conveyor does is it's a current output device that looks at the voltage across its Y and X terminals, and as a result of that voltage puts the same current as goes out of the output terminal into the X terminal. So it's a long way of saying it's kind of a transconductance stage. So what the schematic is showing you there is that we use this transconductance stage to basically take the voltage domain of whatever you plug in, mic, whatever, and then we take that to the current domain, and then we take that back to the voltage domain on the output. So you can ask why we do that. So there's a couple of good reasons that we do.
Why?
Yeah, right. So the first thing is, if you think about common mode. So again, back to the common mode problem that we talked about. Because this doesn't have a secondary stage that's in the voltage domain, it doesn't let through any common mode signals to the second stage. Basically, if you have the same signal on the in minus and in plus terminals, there is no net voltage across RG. If there's no net voltage across RG, you don't get any currents out into the A3 stage anymore. So basically, any common mode is just killed at the input. So now you've kind of got around that whole additive problem with the internal nodes saturating that we came across before.
So in lay terms, that's eliminating interference for the average viewer.
Basically, yeah. Because you're in a current domain, then there's no voltage swing and clipping problem, right? You're not hitting those end stops. So the combination of differential and common mode, all the first stage does now is react to differential signals, so the wanted signals. It doesn't react to any common mode signals.
Okay.
Yeah. So the other thing it does is it basically, by varying RG against RF, the two feedback resistors, is that you can basically go seamlessly from gain to attenuation. You don't have this setup where you get to unity gain and then you have to attenuate somewhere else. As you vary RG against RF, then you can go from high gain, from low noise high gain, up to quite high attenuation levels just by increasing RG. You just keep increasing it, and that ratio of RF to RG basically defines your input gain at that point.
So meaning that RG could be less than or greater than RF, making it
exactly
multiplier or divider.
Yeah, you got it. And then the other thing not shown here, but what we do is we allow that the first stage runs off. The current conveyors run off really high rails, so you run those off plus or minus 18, plus or minus 15 volt rails. So that means that that they can track any it's kind of large signal coming in. And then the second stage, the A3 stage, is run off the same rails as the ADC. So number one, that saves power, but number two, it means that even if the user sets the gains wrong and you clip A3 and that saturates, it'll never overdrive the ADC because it's run from the same rails and biased up to ground and whatever the ADC is running off. It's biased to the same rails as the ADC, so that kind of helps out as well. And so this is kind of a kind of application diagram of what it looks like in practice. The chip itself is a 2-channel chip. If you look at the components around it, it's very sort of light on support components.
Yeah.
The gain is set digitally. There's a SPI interface that kind of sets the gain there, and does a few other things as well. When we change gains, we use a zero cross detector. So if you change gains on a sine wave quickly, you can get this kind of zipper noise, step functions. That makes sure that when you write a gain change, it waits till the sine wave kind of goes through a crossing before it changes the gain. So that helps enormously in changing gains again seamlessly without having artifacts coming through.
So in systems that are going to implement this solution, do you know in advance the signal range that you're going to get on your input, and you design it for that?
So the way the thing itself has the gain ranges from minus 18 dB to plus 47 dB in 1 dB steps. So depending on what the gain depends on in its system depends on a bunch of things, right? What your ADC full scale is, any other kind of digital scaling that you have after that as well. But the input stage again is designed to work up to plus or minus 18 volts, and then it can work down to plus or minus 6 volts as well. So if you're designing an audio interface, a desktop box, you're probably not going to have 18 volt rails. So you can use plus or minus 6 volts, and you wouldn't need, it wouldn't work with as much attenuation. It wouldn't deal with such big signals coming in. So you wouldn't use the full minus 18 dB of that. But then you could scale it up to give an appropriate system headroom as you need for that.
So ultimately, what you want to do is try and fill up the full ADAC dynamic range based on whatever signal you've got.
Exactly, and that's the name of the game.
And depending on each input, you is going to set the gain individually. So this is a pure electronic signal,
right,
high scale, and
right. And typically on a console, you have lineup levels of zero. Jesus, can't remember. Plus 4 dBu. So yeah, you set the gains appropriately depending on how much headroom you had in the console. 20 dBs of digital headroom on the digital side, or 18 dBs of digital headroom on the digital side. So it allows you to do that sort of super conveniently, basically.
Yep. Okay, and then you said minus 40 dB to plus something in 1 dB increments.
Yeah, minus 18 to plus 47. So,
minus 18 to plus 47 in 1 dB increments. So it's pretty high resolution in that regard then.
Yeah, I mean it's you can obviously use less than that if you need to, but like looking at a number of systems, talking to customers about this, 1 dB resolution seemed to be good enough for all kind of thing. So.
Yep. And what does that equate to in terms of an input signal voltage, peak to peak, for example? The range becomes as low as then 10 millivolt or something signal from a microphone directly.
Yeah, so
you don't have to preamp your mics up. You could actually just apply that gain right here. Is that
exactly. I mean, it's got. I mean, you got this thing where, so if you got 47 dB from this thing, right? So if you just basic stuff, if you think about if you have a 2 volt RMS ADC input, 40 dB is 100x. So you've got so get that right. Hang on. So that's 200 millivolts, 20 millivolts full scale, right? Okay. So a typical microphone, a condenser mic, is going to be that'll be fine for a condenser mic. If you need more gain than that, at that point and this is super nerdy stuff here, but we'll get into it. If you get into the front end noise of what limits the noise floor, right? What at 47 dB is the front end devices of the 5510 will limit the noise floor. So we could add more analog gain, but you really wouldn't get any more signal to noise. So at that point, what you do, or what many customers do, is add digital gain, right? So if the signal is so small and you're at full gain, it doesn't really matter if you add analog gain on the front end or you just scale it up digitally to get full scale. So above about sort of 30, 40 dB, then it doesn't really matter where you add the gain. So
implying that your signal is right near to the noise floor anyway, so there's nothing to be.
Right. And so we could design it to add simply more gain, but then the die size gets bigger and the cost goes up. So it was it's a trade-off kind of thing for that.
And so in these applications, you get an SPI interface to drive the gain controller. So therefore, you must always have a controller MCU or chip running these things.
Yeah, I mean, typically, you'd have a micro that's sitting there, you're running the rest of the system. I mean, usually on the pro side, you set the gains and you're reading an encoder or a pot to set the gain. SPI writes it to this thing. A lot of the time, it's not updated, right? Once you've set the gains for a session, it doesn't. It gets trimmed occasionally, but it's not a constant kind of write. Yep. The other thing we added just to allow greater flexibility in system is we put some GPIOs on this as well. So, if you want to light an LED to say you've got phantom power coming up, you could light that and access those via the SPI. And you can read a few things right via the SPI as well. So there's some nice hooks in there for system use kind of thing.
So I was having a look at the block diagram just before, and there's 2 blocks there called DC servo. What does a DC servo do?
Yeah, so what it does is there's as you change gains on this thing, then you're AC coupled at the input, but you really don't want any sudden gain changes to glitch, right? So if you have DC offset anywhere in the system, then it tends to, as you make a gain change, you get this kind of transition, and you hear that as a click. So what you do is, or what this thing does is, as the front end has a slight amount of offset, what the DC servo does, it looks at that offset on the actual output of the thing before it hits the ADC, and then injects a tiny current into the middle stage, into that middle current node, and it just corrects for that DC offset. So any gain changes don't appear very loud and clicky. So
that acts as essentially as a feedback system of offset.
Yeah, exactly. It just removes offset, and so as it settles out, as you set a new gain setting, it'll settle out and then remove that offset as well. So typically, the ADC itself has a DC removal thing, so you don't have to strive for microvolts of offset on the output, but it's kind of a nice to have because it does stop the gains making a noise as you switch the gains.
Yep. In this example, there's input DC blocking caps. That's not necessary though. Depends on.
Yeah, I mean, not shown here. I mean, most systems go for DC blocking caps on the inputs because it's just a comfy blanket thing a lot of the time. But the most important thing is if you have phantom power. So pro systems tend to have, like for condenser mics, you have this 48 volt button you press. So that does nasty, I mean, it powers up the mic, but it does nasty things to the rest of the system. So the mic amp can't tolerate 48 volts. So those caps protect the input from kind of having to have to operate plus 18 volts or 48 volts. So AC coupling is, that AC coupling is usually mandatory for the systems.
Okay. And microphones is getting a lot of coverage in this case, but are there other input devices that also present specific problems that this solves?
Yeah, I mean, there's subtle stuff. I mean, if you plug in a single-ended source to this thing, if you just ground one input,
okay.
The instrumentation amp thing it does a weird thing in the middle stages. It kind of half amplifies the common mode. It kind of treats it as half common mode and half balanced. So it has weird headroom issues as well. But in our case, if you plug in something single-ended, it only amplifies or passes forward what's asserted across that RG resistor. So it's a great way of like balancing up a single-ended source. So as it presents to the ADC, completely balanced source. So you're good there. The other thing it does is to reach the noise levels that we have for microphones, especially. A lot of people use bipolar transistors on the input. That typically has limitations on bias resistors that you have to put externally. You can't put 1 meg bias resistors on it because the base current for the transistors swamps them out and it just sort of rails itself. So you're stuck with this lowish impedance. We actually use FETs for the CMOS FETs for the input to get the low noise, massive CMOS FETs, which means you can rig these things to have high impedance. So you can that R11 2.2K there, you could make that much bigger. So you can get away a lot. I mean, some systems have this thing where you have like a mic line, mic input, and then a line input, and they switch separately or whatever, which takes up a bunch of space on the back panel. What you can do now is basically have it switchable, or even have just a set high impedance and get on with life, right? And just have one socket that deals with everything. So
very cool.
So from a system approach, I'm curious because I bought these boxes before, and they're like bulky boxes for a mic preamp. How much space are we actually eliminating? Like, is this a cable end implementation, or is this still a box? Like in terms of the productization, so you guys are eliminating a lot of parts.
So if you look at this, so this is our CEVB. Which looks and so this is the eval kit you can buy right now.
Okay.
It looks enormous, right? But really, the part that the part that is our chip. Let me show you. laser pointer is. Can you guys see the laser pointer? I can't
Yeah,
see the laser
yeah,
pointer.
yeah.
Hang on. It's there. So that's
Okay.
us. So these are the components around it, right?
That's it.
This is basically it. That's the mic preamp. The XLR sockets look enormous. They're an inch wide or something. There's some input caps here, and we used expensive input caps because we wanted to test nicely.
Right.
But most of the support circuitry is just that area right there. So
Yeah, it's almost like a little cable end. To be
right.
fair, like,
I mean, you compare it with like a big channel. You got all the XLRs or whatever they are. Then this can sit. This deals with 2 XLRs, so it's tiny as a solution.
So I was just in general curious a little bit about digitally controlled gain adjustment. How does that actually work?
In terms of like the nerdy kind of how we switch resistors and stuff.
Yeah.
So, well, let's get out of this. Let's go back a few slides. So that RG right there is really a string of resistors and some FET switches that switch in, switch out a lot of the resistance as you go up in gain. And the way we do
a digital word is flipping and any number.
Exactly. So that RG there is moving around in response to a register right from the SPI, and then that will switch out certain resistors. We also move RF around as well. So we get like the 1 dB steps are done in the second stage, and we have chunkier steps at the first stage. So we have a user combination, and it keeps the reason we do that is it keeps the area down on the die, so it makes it a little bit more again cheaper and smaller.
I guess also keeps the resistor values from being too crazy and small or large.
Yeah, exactly. I mean, they have to get necessarily small because RG contributes to the input noise of the thing. So so a lot of the complexity in the the special source is in switching it out without affecting the linearity and stuff. So some of the FETs that switch it out have to be linearized, and and there's some effort that goes into that and some die area as well. So it's not trivial. But
this one about the gain change step being made at a 0 cross. Is that quite important? Because it's not being done on the fly when you're actually recording anything. This is only when you're be setting up your signal level. Is this a nicety, or is this something that's quite important?
You nailed it. Yeah, I mean, it's people who are evaluating your part will draw attention to it and say, look, if I change the gain, it does this. So, in reality, in use, as you correctly point out, usually your gains are set. You typically mid-session, you're not touching the dials, right? You're writing the faders, but not the gain on the input. So, yeah, you're correct. But yeah, I mean, it's. But still annoying when it happens. So
it is part of listening to the customer base. So we had a lot of customer input in the features definition. There are some few data converters that offer that 0 cross detect in it, and by us including it, it allows them to basically use any pro audio ADC they want. So we're sort of agnostic. So ours will work with anybody. It gives them an opportunity to source and supply what they want, and they're not limited to using one data converter because of one specific feature.
Yep, exactly. And so the application, is this going into kind of like mixing desks, bigger panels that have a large number of inputs, or is it more for, you just showed the evaluation as a 2-channel system?
Phil, do you want to talk about customers?
This part at the current time, we're seeing a pretty wide range. I mean, we have customers in the high-end leadership pro audio live sound area that's essentially ramping to production. We have people in the more the B2B, conference room space. We have people that are creating product for churches, schools. We also have some customers that we're engaging in the area of more podcasting equipment, things that are more consumer-like. So I would say the range of customers in the audio, I'm going to say pro audio, prosumer audio area is quite wide. and it seems to be growing by the day. We're getting a lot of very good responses. We've had a few customers do the evaluation and start production much faster than I'm used to, certainly in the other markets that we play in. So,
And anything like bizarre? I'm always fascinated, like industrial noise detection and stuff like this, like for alignment detection in factories or automotive. Anything interesting that you can mention?
Yeah, I mean, you mentioned industrial. There are applications for this for industrial stuff, right? I mean, some of them are DC centric, so they need the kind of full DC coupled path.
Right.
But there's some stuff out there that just uses instrumentation amps, and they value, especially industrial environments, the amount of I can't emphasize it enough the amount of common mode rejection this part gives you, right? Especially at high gains, you can tolerate tens of volts of common mode at the same time as amplifying a tiny signal. So that perks up the industrial guys because they, long cable runs, factories, all that kind of stuff, and your motors running around. So that gets the interest there. But definitely industrial. That's kind of
Cool.
more to come on that front, I
we
think.
refer to it as a universal analog front end. I mean, yes, we put some features that were very tuned for this pro audio area, but we do. Our goal here was to be successful, create a high-valued, emerging, innovative part, if you will, very novel, cost-effective. I think we've achieved probably the highest level of integration and very low power. We've really solved a lot of problems and just kind of nailed it right in the pro space. Now we have to execute and engage customers, and that's happening. In parallel with that, right, we see these industrial, even medical, there's various other markets where they want the precision and that high-end performance of the data converter that you get in audio, but they're different environments. And so by having this very wide voltage and dealing with the noise, we're excited about that. We see it going sideways as much as deeper in the audio space. So there will be more things coming as we move forward.
I would say, as much as we love audio, it's still got to be. It's a pretty tight community. So you got to spread your wings pretty wide to try to make it commercially successful. You got to cover some more bases.
Yeah,
sure.
Yeah, but specifically to David, to your point, I mean, there's so many nuances in the audio that if you don't get those right, you're not going to say.
Oh, they're fussy. They're fussy. Just listen to Simon's questions.
Right. So yeah, for this we tried to get the audio right to start with, then with a focus on the rest of the medical industrial stuff.
Cool.
Excellent.
And we got some more. I mean, this is first of a few products that we're doing for audio. I mean, I think the pro audio market generally has just been underserved in terms of silicon for some time, right? I mean, you look out there, what other mic amp chips are being used? There's a few from the big guys, but some of those are 20 years old, right? They're literally decades old, and they're still being designed in. I mean, I think a lot of it is like the consolidation on the large analog companies, right? That they just get into these big company kind of modes, and to make a difference on the bottom line, they can't launch products for smaller markets, right? So it doesn't make a difference to a $10 billion company, right? It really doesn't. But for us, as a tiny but perfectly formed semiconductor company, this is great, right? It's blue ocean for us, and we can bring value to these guys who use it. So.
Cool. Okay. Where can people find you? Do you guys like hang out at NAMM now? Are you guys like rocking a Fender and demonstrating the pickup range of these things? We actually like just to byline it, like we love the NAMM show, but it's not really commercially viable sometimes. But you guys feel like it's a good market to like pursue, and like anyways, the point is, where can people find you next?
Well, we were at NAMM. We've been at NAMM for a couple of years, but this was the first made public announcements. So we had a lot of customers there. So it was a big show. ISE, Barcelona, we were there. You'll find us at Infocom.
Okay,
We have a bunch of
is that in Vegas this year, or where is it?
Infocom is Vegas this year. Yeah.
In June, right?
in June.
Okay.
Um, yeah, so those are some of the shows that we tend to go to. There are a few more, I would say, not niche, they just have a different flavor of customer to it, but AES and NAB, et cetera. But the main shows for us are going to be NAM, ISE, and Infocom,
Okay. And
as this product in this market. So
Okay.
for the industrial guys, it goes other places. From a Triad perspective, we have a little bigger umbrella or coverage with our ASIC and other products. So we do things all the way from virtual reality to high end comms. I was just down at OFC in Southern Cal. So you'll find Triad in many places, but for this product and this focus, those are the three big shows.
Okay, cool. All right. So we'll put some links below for people to find out more. And yeah, any more questions, Simon, before we say goodbye?
Perfect. Thanks.
All right. Okay. Phil, Tony, thank you so much for joining us today. We appreciate it. That was an excellent introduction to this part, and we encourage people to follow up with more and like, subscribe, all that good stuff. So thanks, everybody. We'll see you on the next episode.